Hello and welcome back to CS422, Theory of Computation. Today we're going to have a recap of chapter 4 about complexity theory and reduction, structural complexity theory. And then we will start with chapter 5 on advanced topics in computational complexity theory. So let's look at the notions of reductions and how we've applied them to various problems to compare the computational complexity of problems whose computational complexity we don't know, but which we were able to compare. And so here's, for your convenience, a reminder of the notion of reduction, which is a refinement of the notion. Polynomial time reduction is a refinement of the notion of a qualitative or computable reduction. And whenever you're asked to prove some reduction, please remember the 4 steps. First, to specify the reduction function. Second, make sure that it is computable in polynomial time. Third and fourth, make sure that this equivalence holds, namely the if and only if the positive instances get mapped to positive instances and negative instances get mapped to negative instances. So, and we've applied that to a very basic example, namely to compare clique and independent set first. And here the reduction was simply invert the graph, which means invert the edges, which means whenever there's an edge present, remove it, and whenever there was an edge absent, add it, which is the same as saying kind of flip the bits in the adjacency matrix. And it was easy to verify that this can be done in polynomial time. That is the second step. And the third and fourth step, also easy. Of course, whenever there's a clique of size k, here in this case example, clique of size 4, indicated with red vertices, then in the complement graph, these 4, the same 4 vertices are pairwise disconnected and vice versa. So that's the first example. And thus we were able to establish that the 2 problems have basically the same computational complexity, although we, and actually nobody knows what is that computational complexity. Then we've moved on to more examples of reduction from independent set, the graph problem we just mentioned, to Boolean satisfiability, namely given a Boolean expression, does it have a satisfying assignment? And this was kind of interesting, more interesting, because it involves some construction and some analysis. Namely, we have kind of encoded properties of a graph, namely having an independent set of size k, in terms of Boolean formulas. And such techniques actually are interesting in many other areas as well. So they are of independent interest. For example, many problems can be solved automatically on the computer by using a Boolean solver. They're very efficient Boolean solvers, highly parallel. So that means when you have a problem in a different realm that is not about Booleans, but you can reformulate that problem equivalently. That's important. Reformulate that problem equivalently using Boolean expressions. Then you can feed the latter Boolean expressions into the solver. Another perspective of that reduction is that the computer basically operates on bits, that is on Booleans, right? So intuitively, it should be possible to formulate other problems as problems over the Booleans, because other computational problems at the end of the day, they are solved on a computer using Booleans. And here's an example how to do that explicitly. And another subtle point here is, no, I'll get back to that later. So how did we do that? what is the lesson to be learned here for your future assignments about polynomial time reduction is to first come up with an idea what should be the meaning of the Boolean variables. And the first naive idea is to make Boolean variables that correspond to the independent set, that is maybe k variables, one for each independent vertex, and then try to make expressions that say these variables or the vertices they represent are indeed independent. The problem with that first naive approach is that in this case, a variable representing a vertex cannot be just Boolean, right? Because there are n vertices. So a variable would be like an integer between 1 and n. But we want to create a Boolean expression with Boolean variables, and the Boolean variables can only have values 0 and 1. So another idea or attempt might be to encode the vertices, the integer, the number of the vertex in binary. But this turns out to be very tedious. So here we therefore have followed a third approach, namely we have introduced many more variables, k for the vertices and additional variables, one for each vertex, so that the variables are now indexed by pairs, vertex and number, so that this means the vertex v is the ith vertex in a purported independent set. And now this variable has become a Boolean variable. Either the vertex v is the ith vertex or not, yes or no, that's Boolean. So that's an important first step in where really some idea is required. And then express in Boolean expressions all the conditions that we have. So for example, vertex v cannot be simultaneously the ith and the jth vertex in the independent set. This is what we formulated in the second family of Boolean expressions, clauses actually. The first family of Boolean expression captured that some vertex must be the ith vertex, which is expressed with this huge disjunction. And finally, the third family of Boolean expression captures the being independent, so that whenever there's an edge between vertices u and v, then not both can be part of the independent set, not both can be ith or jth vertex at the same time. So this is another interesting technique how to express properties about other universes here, for example, graph, the structure of graphs, in terms of Boolean expressions. Okay. And then we've analyzed and made sure that it's all done, can be done, computed in polynomial time. Then we've performed some reduction from 4 satisfiability to 3 satisfiability. This was interesting because a Boolean expression in 4 conjunctive normal form cannot be equivalent, cannot be converted equivalently into an expression in 3 conjunctive normal form. But we don't really require equivalence for Boolean expressions here. We require satisfiability equivalence. If one is satisfiable, then the new one must also be satisfiable, and vice versa. And this observation allowed us to introduce more variables for the expression in 3 conjunctive normal form, so that these new expressions with the new variables can finally become satisfiability equivalent. And this is what we did. We introduced new variables in such a way that the new variables kind of act as fuse. We split the clauses with too many literals and introduce new variables as fuse that make sure that whatever the new variable is, it can make at most one of the two split clauses true, and the other must be true by itself. And being true by itself means that there was also the original clause was true and vice versa. So that was also an interesting technique to keep in mind. And finally, we had an example of a reduction where we actually started with Boolean expression and have expressed properties of this Boolean expression in terms of graph properties. This is if you think about it, Boolean expressions are pretty universal, but expressing Boolean properties using graphs, that's highly original. So here's a construction that I'd like to recall. And here, this construction heavily made use that we can start with a Boolean expression in 3 conjunctive normal form. Namely, this Boolean expression, a conjunction of clauses where each clause is in 3 conjunctive normal form. We would convert each clause into a triangle, so that this is a click, 3-click, and this is another 3-click and then another 3-click. And this is designed in such a way that it's impossible to have a dependent set that contain 2 vertices from within a triangle, because triangle being completely connected means any 2 vertices within a triangle are connected and therefore not independent. So the only chance to get an independent set from such a graph with such a structure is by picking 1 vertex from each triangle. And so the largest possible independent set has size k, where k denotes the number of clauses here and the number of triangles here. And so that's where we started with, and then we added edges that indicate the actual structure of the clauses. Namely, if a clause, 1 clause corresponding to 1 triangle contains a variable, and another clause corresponding to another triangle contains the same variable negated, possibly at a different positions, or each of the 3 positions correspond to each of the 3 possible literals. So if 1 clause, here's an example, the first clause contains the variable u, the second clause contains the variable u negated, then we would draw an edge from the first vertex to the second vertex. And similarly, here there's an edge from here to here, because this here, corresponding to the last clause, contains a variable, and this contains the variable negated in this position, this in this position. So that's where we add an edge. We don't add an edge when there's a variable that occurs both negated or unnegated. So here between here and here, there is no edge, nor is there an edge from here to here, only when there's a negation. Okay, and hopefully you wonder why do we do this in such a way. Actually, this idea is due to Richard Karp. Why did he construct the graph in this way? The reason is that now this kind of captures the independence of the variables, right? So because in the end we want to show that the original Boolean expression has a satisfying assignment if and only this graph has k pairwise independent vertices, then this makes sure that vertices that are have an edge are not independent. That is, vertices that correspond to literals that occur negated, and therefore we cannot assign literals simply the value true. That's a kind of a general strategy, right? In order to show that a Boolean expression is satisfiable, the easiest way is to just assign the value true to each literal. So assigning true to a variable and assigning true to a negated variable, that means assigning false to the original variable. And if we can do that, then of course all clauses are satisfied, because even all the literals are satisfied, and therefore the disjunction of the literals, and therefore the clause. But this is not possible in general. If we have this literal and we have this literal, then we cannot simply assign true to this literal and to this literal, because they are not independent, right? One is the negation of the other. We can assign true to this literal, and we can also assign true to this literal because it's the same. But this we cannot do that assignment when one literal is the negation of the other. They are not, in this case, they are not independent. So assigning true to both of them would violate well definition. And this is exactly what these additional edges here capture, that these are two vertices are not independent. These two vertices are not independent because one is the negation of the other. And this in turn means, once we have added all these edges, that the remaining vertices are independent. So for example, these two vertices are independent because there is no edge. And when they're independent, then we can assign simply true to both literals, the literals corresponding to these vertices, and thus arrive at a satisfying assignment for every choice of k independent vertices, and vice versa. Whenever there is a satisfying assignment, then this gives rise to a choice of k independent vertices, and thus we were able to verify the last two conditions of a polynomial time reduction here. Okay, so this was a last example, and thus we have been able to establish and classify many problems whose computational complexity we don't and nobody does know to be equivalent. Let me hear some examples. Click, independent set, satisfiability, 3 satisfiability are all polynomial time equivalent. And this leads to the definition of the hardest problems in this class NP. These are problems to which any other problem can be reduced in polynomial time in this sense. And for now, this is a nice definition, but it's empty, right? So it's not at all obvious that there is such a hardest problem, right? So if you think about it, if you think about reduction as a partial order, then in many cases there is no largest set, no largest element. For example, in the natural numbers equipped with a less or equal relation, there is no largest element, right? There is no largest natural number. And the same could be possible about the complexity class NP. There could always be problems that are maybe just a little bit, but strictly larger. There could be an infinite sequence of strictly larger problems in this complexity class NP, in which case there would be no hardest problem, right? So it was important when Stephen Cook proved that there exists such a hardest problem, maybe the Boolean satisfiability problem. To this end, he proved the master reduction. He was able to reduce any other problem in NP to this Boolean satisfiability problem, and thus established that there are hardest problems. And based on the classification we obtained earlier, that means that also 3 satisfiability is a hardest problem, independent set is a hardest problem, click is a hardest problem, and many more problems are hardest problems, namely equivalent, equally hard as satisfiability. That's what we established before. And this gives rise to this picture. There's the class P of polynomial time decidable problems. Then there's a class NP of polynomial time verifiable problem. And in this latter class, there's a subclass of hardest problems in NP, indicated here in dark blue. And these start problems are, by definition, all mutually polynomial time equivalent. So we've established polynomial time equivalence for several such problems, but here there are many more. And I want to extend that, namely to consider also the class co-NP. This is similar to our investigation about the arithmetic hierarchy, problems that are recursively enumerable, that are semi-decidable. And we've considered problems whose complement is recursively enumerable, is semi-decidable, and we call them co-recursively enumerable or pi1 problems. And similarly, here in the refined view of computational complexity, we have considered also co-NP, that is the complement of problems that are polynomial time verifiable. And beyond these two classes, there's a larger class of p-space. Remember, all small hierarchy, the class of problems that can be decided in polynomial amount of memory. And we will see that also in this class, there's a subclass of hardest problems. This is the next chapter. And by our hierarchy, this class is in turn contained in the class EPS of exponential time decidable problems. And then there's a hierarchy between the so-called polynomial hierarchy, which will be the subject of the next chapter as well. So now remember the P versus NP millennium problem, asking whether P is equal or different from NP. And this is still an open problem. Now let's suppose that P is equal to NP. What happens? What are the consequences in this case? If P is equal to NP, then this complexity class collapses to be equal to P, right? And therefore NP complete collapses along the side. So NP complete means then becomes equal to P, right? So that's an interesting observation. If P is equal to NP, then this class collapses and becomes equal to NP complete. So then any problem, polynomial time decidable problem, is NP complete and vice versa. And actually in this case, also the polynomial hierarchy here collapses, whereas this here may still be different. So this is one scenario. So one scenario is that P is equal to NP. If P is different from NP, it's kind of the interesting scenario that most people would bet on these days, then there are still some possibilities how the overall picture looks like, right? So let's recall that the terminology co-NP are the class of the problem, the complements of problems in NP, the class of problems whose complement is polynomial time verifiable. And if it is, well, P is equal to co-NP, that's important to observe here. Well, because P is deterministic, so we can easily decide the complement of a problem by taking the while plus program and flipping the outputs when it terminates. Everything is deterministic. This is the difference to the non-deterministic setting, where computation can have several computation paths. Remember our notion of a non-deterministic while plus program. So if P is different to NP, then there could be one important thing to observe is that whenever a problem is NP complete, then its complement is co-NP complete in the sense of Cook, namely it is maximal. Any other problem in co-NP can be reduced in polynomial time to this problem. So that means there's a kind of duality between these problems, more specifically bijection. In this case, one can actually show, and actually later did prove, that then there are problems that are strictly in between. Problems that are maybe belong to NP and to co-NP, yet problems which are not polynomial time decidable. This proof requires some advanced diagonalization techniques. Another scenario is where P is different from NP, again different from NP, but NP is equal to co-NP, right? You see the difference between these two scenarios here. NP and co-NP are different. There is a common intersection, a non-empty intersection, or the other scenario, they are actually equal, but still it's possible to be different from P and co-NP. When P is equal to co-NP and NP is equal to NP, then everything collapses. But it's quite conceivable that only these two collapse. So these are different scenarios for how P, NP, co-NP could be related to each other. Right. And then we discussed the master reduction of Cook. Maybe we've reduced any problem in NP to the Boolean satisfiability. And there's something more to be said about that. Last time we didn't have enough time, so let's do that. So the basic idea is to right. So there are two perspectives. Remember, there are two perspectives to NP. One is the syntactical set of problems which is defined with this witness. The other perspective is this with this non-deterministic while plus programs. And in both cases, there's the witness. In the first case, it's explicit. In the second case, it arises from all these guesses, right? And the idea is now to make these witnesses correspond to a satisfying assignment in a Boolean expression. So how can we do that? That means the Boolean expression should kind of simulate the computation of the verifier, except for the given witness, that is, except for the guesses of the program. So to this end, that means we need to somehow express and encode the deterministic part of a while plus program, the part that is not related to guessing. We need to encode that as Boolean expression. And again, basically that should be no problem. That should be possible because the computer, your computer, does operate on Booleans, so it should be possible to express computation using many Boolean expressions. And I refrain from repeating this construction of the Boolean expressions here, but want to recall and convey some intuition about that. So this is what we did. We've constructed Boolean terms for each of the commands in the while plus program that decides, that verifies the given problem under consideration, the problem in NP, right? So we're talking about the generic, the mass reduction. Being in NP, it means it is polynomial time verifiable, which means there's an algorithm or deterministic while plus program which actually performs that verification. And then we encode the computational steps of that program as Boolean expressions, so that with the exception of these guesses, the program represents exactly the computation of the verifier, and the guesses or the witness that then becomes the satisfying assignment if it exists. So that's the basic idea. We've also discussed a more general and more generic complete problem, namely expressing the very statement. The while plus program A terminates, non-deterministic while plus program A terminates when presented with some input, and we've expressed that yeah, as a generic NP-complete problem. Right. And finally, another polynomial time reduction is two subset sum. Okay, and now having proved the master theorem, in order to show subset sum NP complete, we can make use of the things that all have already been proven in the master theorem, namely with already established Boolean satisfiability and thus also 3 satisfiability as NP complete. So in order to prove subset sum as NP complete, we don't have to perform another master reduction. We can use that we've already established 3 satisfiability to be NP complete, and thus it suffices to reduce 3 satisfiability to subset sum, because then by transitivity, and since 3 satisfiability is already known to be NP complete, it follows that also subset sum is NP complete. So any other problem, first show that subset sum belongs to NP, and then reduce any other problem in NP first to satisfiability according to Hooke's theorem, then from satisfiability to 3 satisfiability, based on what we've just discussed, introduce new variables, and then from 3 satisfiability to subset sum, which is what we're now going to do and show. So here you see the formal specification of subset sum, which asks, given certain weights A1 to AN and bound B, is it possible to fill a knapsack with a subset of the weights, right, of the packets? So the subset being indicated here by these bits. Is it possible to fill it and thus arrive at perfectly filling the subset exactly as far as it can bear, namely it can bear up to weight B. Okay, and here for this reduction we've applied another very interesting type of reduction, namely actually it's a strong polynomial time reduction. I'm going to explain that once we've recalled it, but the idea is again now to somehow express Boolean properties now as equality of large numbers. So equality of large number has the benefit that if the large numbers have some block form, so like some integer, and then there's a large number of zeros, and then there's another integer, then we'll kind of recover these integers or compare these integers among themselves simultaneously, actually, in this way, this equation, right? So here's the idea. So we reduce 3 satisfiability to subset sum, and to this end, we convert a given assignment in 3 set conjunctive normal form. Here 3 variables, here 3 variables, here 3 variables. Some variable occur repeatedly, like x5 occurs here and here, and then express all these properties using kind of a number theory, basic trivial number theory. Namely, express first, so the existence of a subset here of the variables should correspond to a satisfying assignment. That's the idea, that's the goal. And we do that by expressing the subset as a subset of the variables. So we artificially create values here, A1 to AN, these are the V's, and they're also going to be V primes. with the ideas we want to express first that so that's the idea, the intuition, that's the important part. So choosing one of the variables, let's say v3, and putting v3 into the equation, that is choosing alpha 3 to be 1, should mean that we make the third variable true in a satisfying assignment. Whereas choosing v3 prime should mean that we choose the third variable to be false in the satisfying assignment. So each variable, v3 or v3 prime, kind of corresponds to a Boolean value of the third Boolean variable x3. And this third Boolean variable can be either true or false, but it must be at least one of the two. Otherwise, we haven't assigned a value to it. And it cannot be two of them. So that translates to the condition that we want any such subset of these values to have precisely one of v3 and v3 prime in this sum, precisely one of v2 and v2 prime in this sum, and so on, so that this sum kind of is forced to pick precisely one of v1 or of v2 1 prime, precisely one of v2 and of v2 prime, and so on. And how do we do that? Only using one equation, one arithmetic equation. So the first thing to this end is to consider this number in decimal. So that making them in decimal will show to prevent any ambiguities through to carrying. Okay, so decimal means that there's so many additional digits available, 2, 3, 4, 5, before a carry occurs to the next larger digit. We want to compare these digits independently, and in particular, we want precisely one of these two to be feasible in a sum, and thus we've placed a 1 here and 1 in here, so that we're going to impose that the sum value must have a 1 here. This kind of forces that at least one of these two variables is chosen. If we choose none of them, then there will be a 0 here. And because there's no carrying, this 0 cannot be converted to a 1 by any of the other variables, because the other variables only have zeros here in this position. So the only way to get a 1 in this place is by choosing one of the two, but only one of the two, because otherwise, if we choose both, then there would be a 2-digit here. So this is a kind of trick how to express a conjunction of actual simple Boolean expression, choose precisely one of the two, as one single equation in a higher numeral system. Okay. And similar for the second variable, make sure that precisely one of the two variables is chosen by enforcing that the next digit here at this position is 1, and putting 1 here and here, so that when there's an equality here, this equality, that means that precisely one of the two variables has been chosen, and our interpretation, our intuition that we're currently encoding formally is that this corresponds to choice. The second Boolean variable x2 is assigned true or is assigned false, but not both, though none of the two. So this is kind of explains all these digits here that make sure that when the subset is chosen and equal to this carefully crafted number, then all these ones here enforce that precisely one of the two variables here has been chosen, one of these two variables has been chosen, and one of these two variables has been chosen, and so on, right? Now, what about the remaining digits in front, but we want this the choice of variables in the subset to encode satisfying expression. A satisfying expression means that at least one literal in each clause must be true, and these 3 digits here correspond to the 3 clauses of the original expression. If there are more than 3 clauses, then there will be more than 3 digits. If there are more than 5 variables, then there will be more than this, so that the total decimal length of all the variables in a satisfying assignment is length n plus m, decimal length. N here for the variables, m here for the clauses. Okay, so that's the idea. And yes, making a clause evaluated true requires that at least one of the chosen variables has a digit 1 here, meaning that it occurs in this clause. So here, for example, x1 occurs in this clause, x3 occurs negated in this clause, in the first clause, and x5 occurs here unnegated positively in this clause, but it occurs also in the second clause. Okay, so why do we enforce this value of the first digits to become 4? Well, what we want is that it is at least 1. This is expresses that at least one of the literals is true in the assignment, meaning that at least one of the variables here has been chosen in the equation. But the clause is true also if 2 or even 3 of its literals are true. So we want to kind of express here that every single digit should be at least 1. But we cannot express that because the definition of the problem asks for equality, not for inequality for greater or equal. So how can we express greater or equal as equality? By adding additional dummy variables that allow to kind of top up any value that is greater or equal 1 to become equal to 4, but only those values that are already greater or equal to 1, not the values that are less than 1, that is the values that are 0. And to this end, additional dummy variables are introduced that allow to top up every single position by at most 3, by 1 or by 2 or by both of them. And the same for the next position corresponding to the next clause, and by the third position corresponding to the third clause. So all these together added allow to top up so that whenever there's a choice, a subset of the variables chosen, so that at this position the value is at least 1, then by additionally choosing these variables, one can top up and rate it, thus reach 4. Whereas if variables have been chosen not to be greater or equal to 1, if instead it to be equal to 0, then all topping up does not help to reach the value 4. One can at most top up to value 3. So that's the intuition, that's the idea here. Okay, so that's a recap of all the reductions that we've seen and discussed last time. Now, having had a little bit more time to delve deeper into the ideas, and as you can see, there's no kind of recipe, there's no general method of how to construct such a reduction. There are the 4 steps that I keep mentioning, but the first step, that's the one where all this creativity is required, namely the creativity of how to choose the to create the translation. And here the translation, all the ideas, which variables to choose, what is the meaning, and then kind of apply some rudimentary number theory to make sure that this property that 3 and 4 that satisfying assignments correspond to subsets of the variables that make this equality true and vice versa. Okay, and there's a great question in the chat that I'm very happy about. Thank you very much. So the question asks, if the formula contains 4 clauses, and then how do we choose the dummy numbers? Great question. If the formula contains 4 instead of 3 clauses, then we recall that the front part, our intuition is that the front part will have 4 decimal digits. The front part here corresponds to the number of clauses. And then we'll need additional 2 dummy variables, C4 and D4, which have values 1 and 2 at the new additional front decimal digits and 0 in the rest. Okay, so here we have 1 and 2 at the leading position. And if we have an additional digit in front of that, then we will need 2 more dummy variables that have 1 and 2 respectively at the new leading position. Does that answer your question? It's a great question. Yes, really, that illustrates that you're on the perfect path to understanding what happens if we change something. That's a great approach to really understand that. What happens if we have more variables? What happens if we have more clauses? How does the reduction then look like? And then, of course, yes, I've refrained from really formalizing the reduction, the translation, right? What is the translation now? Translation means input is this encoding of a Boolean expression into 3 conjunctive normal form, and output is this choice of variables with this carefully, so integers with this carefully chosen property that there exists a subset of the integers which evaluate to this expression if and only if the original Boolean expression had a satisfying assignment, right? So yes, these are all the values. And I'd also like to use this opportunity to point out that these values are pretty large, right? So remember, these are kind of decimal numbers. So the values are very large. The binary length, first of all, the decimal length. What is the decimal length of, let's do that more thoroughly. First question is, how many variables do we have in the output instance of subset sum here? A1 and so on up to A, N, and B. Well, we have this B here. And the A's, how many A's do we have? Well, we have 2 A's, 1 for each Boolean variable, right? So for each Boolean variable in the original Boolean expression, in the output instance of subset sum, we have 2 of them. 1 variable and its primed counterpart that indicate that precisely one of the 2 variables must be present to make here an equality. So equation, so 2 variables for each Boolean expression. So that means we have, when they're n Boolean expression, that means we have 2 n variables of this type. And then we have the dummy variables, right? How many dummy variables do we have in this case? Well, we have 2 times m dummy variables, right? Where m denotes the number of clauses, n denotes the number of Boolean variables, and m denotes the number of clauses in the 3 conjunctive normal form expression. And we have 2 m dummy variables here, 2 dummy variables for each position here. And we have here 3 positions because we have 3 clauses, and when we have m clauses, then we have m leading positions. So that answers the question, how many variables are there in the output instance of this translation in the output instance of subset sum? The other question is how large are the variables in binary, right? So if the instances we output here is has binary length that is more than polynomially long, then there's no way to compute this translation in polynomial time, right? We can only output a polynomial length output in polynomial time. right? We can actually produce only output of polynomial length, because in each operation, the length of the data can increase by at most 1, right? So it's important here to verify what is the binary length. And let's here focus first on the decimal length. Why decimal length? Well, the difference is only a constant factor, right? So decimal length or binary, the decimal digit is roughly a little bit more than something between 3 and 4 binary digits, right? 3 binary digits is 8, which is less than 10 for a decimal digit. 4 binary digits is 16, which is larger than 10. So roughly the factor of converting between decimal and binary is a little bit larger than 3, but it's a constant. So it suffices if we can assert that the decimal length rather than the binary length of the output is polynomial. And the output is, well, it consists in encoding of all these numbers. We've already verified that the number of numbers is polynomial, but now how is the decimal length? And the decimal length is m plus n, right? So we have m decimal digits here, 1 for each clause, m the number of clauses, and we have n decimal digits here, n the number of variables, so that the total decimal length is m plus n, which again is polynomial in the input length, which is n plus m at least. So this indeed kind of confirms that behind all this single example, this is just right proof by example, but this example illustrates the general principle, which I leave it to you to really write down explicitly. Yeah, an example says more than 1,000 words or a formula. So this example really illustrates the underlying generic polynomial time reduction, which we've now seen to be computable in polynomial time. Good, thank you very much. And so, yeah, that's what you see. M clauses and n variables for the input Boolean expression results in 2 times n plus 2 times m plus 1 values. The plus 1 is the b here. The 2m are the dummies, and the 2n are these variables. And each one has decimal length, n plus m. So binary length is at most 4 times n plus 4 times n, which is polynomial in n plus m, the input size. Okay, so yes, this is a recap of everything we've talked about here in this chapter 4. But now I would like you to conduct a small quiz. Yes, a quiz, hooray. And also an attendance check. So here's the challenge, the question. In this course, CS422, Theory of Computation, we've considered several notions of reduction. Right now, here we've considered polynomial time reduction, but we've also considered other notions of reductions. And I'd like you to report 3 different notions of reductions that have occurred in this course. For last one, polynomial time reduction is included, so we've already have an answer, but there are 2 more missing. That's part A of the quiz. That's easy. And part B of the quiz is a little bit more challenging. Right, so these 3 different notions of reduction that you're going to report briefly and succinctly, don't write long text, but shortly, write it shortly. There's a combination missing. There's a 4th notion of reduction. And I want you to define that, to fill in the missing definition of a 4th type of reduction. This is like, you know, with cards, right? So imagine you have a deck of cards, right? So like from poker, you have maybe a queen of hearts, you have a king of hearts, and you have a queen of spades, and then some fourth item is missing, namely the king of spades. And if it's missing, then you can see that it's missing and that it's supposed to be here. And the same applies here to this definition. We have three definitions. You can say one corresponds to the queen of hearts, one to the king of hearts, one to the queen of spades. And I want you to observe and fill in the missing definition for corresponding to the fourth condition briefly. So that's what we're going to spend the last 15 minutes of this session. Please write your answers in the chat. Thank you.